the idea is that we're trying to deal with lots and lots of identical particles. And in fact, the formalism allows you to deal with an arbitrary number of them. And the idea is that your Hilbert space becomes what's called a Fock space, which is just a tensor product of single particle spaces. But this tensor product is essentially infinite. You have an arbitrary number of particles, and each one will be in its own. It can be in some particular state, and then, of course, you can have linear combinations of multi-particle states, and you get things like entanglement and stuff. So that's what the formalism is for, is to deal with stuff like that. And if you think about it, we introduced these creation annihilation operators, which create particles in state I or annihilate them in state I. And if you think about this acting on a multi-particle state, say I have this state, right? Well, this is a kind of funny state, right? If this state has n particles in it, then this whole state has n plus 1 particles in it. So the creation annihilation operators actually move you between different spaces of fixed particle number. So that's why it's a little bit tricky, right? It's not. Sometimes, though, you would want to develop this formalism for systems which have a fixed number of particles, some fixed number n. And so that means that if you're constructing operators and things like that, you'd want to make sure that you have equal numbers of creation annihilation operators, right? Because you would want to pop in as many particles as you pop out. So something to keep in mind. So if you want to fix fixed n particles, it means you have equal numbers of creation annihilation operators. Of course, they can be in different states. That doesn't matter. You can imagine, right, a operator that changes the state of a particle. What would that do? Well, that's the same as popping out a particle in some state and then popping in a particle in another state. That's the same as having a single particle transition between states, because they're identical particles. So it doesn't really matter that you like pop one out and pop one back in. They're all identical. So that's how it goes. And so we were talking about operators, and we were discussing single body operators. That means operators that in this second quantization formalism basically correspond to what we would expect a single operator to do on a single particle Hilbert space. So you have those kinds of operators. I'll discuss that in a moment, but remember, the basic idea is that fermions and bosons have different sorts of creation annihilation operators associated with them with different algebras. And we had, for the bosons, just as a summary, we had that the creation annihilation operators commute with each other. And there's also the mixed operators, for which we get a identity unless the guys are in different states. And I promised I would have a better proof of this. I'll talk about the proof of that in a moment. But for the fermions, we had the same thing, but anti-commutation relations. Oh. And you could put little identities here if, to just make sure that we specify that, this is still an operator. It's not like it's a number or anything. So those were the rules. And these are really the only things you need to know for doing second quantization. Everything else is just embellishments on this. Basic ideas are right here. Everything is constructed in terms of creation and annihilation operators, and they have these commutation relations. And the other important thing is that there's a vacuum state, which we denote like this. That's just a state with no particles in it. And so then you can create any state you want by popping in particles in whatever states you want them to be in, and that constitutes second quantization formalism. So I promised I would sort of talk about this one more. We proved all these other ones. So how do you think about this guy? Well, so this one's a little bit trickier, but the idea is you can use the same argument to argue at least that, well, whatever this is, if L is not equal to, and this e to the I alpha is plus or minus 1, depending on whether it's fermion or a boson. But if I think about this combination, right? So if they're in different states, right? If L is not equal to K, then this thing has to vanish, because what does this do? This just pops out a particle in state K and pops one in state L. And we know that if we do this in opposite order, if we pop one in state L and take one out in state K, then that must be the same physical state, right? We haven't done anything. So the only difference between those two things must be some phase, because they must yield the same physical state. And so this thing, at least we know, is proportional to delta LK. So we know that much. But we also know that we can change basis. It's an important aspect to this. Remember, the A's, the creation annihilation operators, are constructed from the single particle states. The AIs, like AI dagger, there's a correspondence between this creation operator and a single particle state, say Ki, right? Because what does the AI do? The AI dagger, well, it pops in a particle in some state Ki that's, part of the single particle Hilbert space. So there's a correspondence there. But we could use any set of states that forms the basis for the single particle state. And we know that these combinations of AIs, they must transform appropriately under that change of basis. So what does that mean? It means that we can take, say, AI, I'm going to change these to AIJs like this. So I'm going to just rewrite this. I can change basis. And if I change basis, what does this do? Well, it'll be a sum over, I'm going to change the AI and the AJ, both of them. So I have to introduce new indices K and L. Then I have some basis coefficients. So I have Ki LK, where these L states are going to be some other basis states in our single particle space. And then this one is for transforming the AJs. So I'm just transforming the I states to some LK states and the J states to some big L sub L states, just a change of basis. And then so then once I do this, you'd have a different set of creation annihilation operators, which I can call B's instead of A's, but they do the same thing, except they generate states that are this big L sub something. But otherwise, it's just sort of, right, comes in the same way. I've just changed variables. And I argued that oh, I see. I have stuff from last time. That's why this thing's a little laggy. Let's see. Oh, that's funny. Anyway, I argued from last time that, or sorry, I just argued, right, that that this has to be, that this whole expression, whatever it is, has to be proportional to delta ij. All I know is, right, if I is not equal to j, then it vanishes. Otherwise, it's something, could be some operator, you know, whatever it is when I is equal to j. But look at this. By the same argument, right, this can't depend on what basis I'm using. So this thing must also be proportional to delta KL, right? For the same reason, I can pop particles in and out of these L states. And these B's should create indistinguishable, physically indistinguishable states, because it doesn't matter which order I apply them in. The only possible difference has to be just an overall phase. So what does it mean? It means that, well, this sum vanishes unless K is equal to L. So I can get rid of the sum over L, say, and then I have K sub I, LK, and then LK, K sub J, and then, you know, these B's. And now, if we think about this, well, oh yeah, and now K is equal to L. So now these become Ks. If we think about this, well, you see in here, we actually have the fact that if we sum over K in here, then we actually get the delta function, delta ij, from the completeness relation. So the only way to have everything be consistent is actually if this quantity here is independent of K, because that's the only way that this then will be able to sum up to give us this delta ij. It's the only way to make it consistent. Now you could probably go in more detail, and you could show that if it's not true, I can provide a counter example where I can construct, what you would do is you could act with this operator on some multi-particle state, and then you could design this multi-particle state such that this quantity is no longer proportional to delta ij. But that's a little bit too much theorem stuff, I think. So I think at least intuitively, you know that this whole thing, right, if I'm allowed to sum over K, and if this is independent of K, then this just gives me this delta function no matter what, because of the sort of orthonormal, because of the completeness properties of the single particle basis states. So you can conclude from this that this thing must be independent of K. So whatever this is, it can't depend on the particular state it's in. And so it's highly constrained. There's only, you can figure out what it is by acting with it on some state that you already know about, such as the vacuum, which is the argument that I presented before. I just took this thing and I acted with it on the vacuum and showed you that it has to be the identity, right? But, this is a little bit more mathematics to show you why it's sensible that that's the only possibility for this kind of operator. So hopefully that helps you a little more in terms of convincing yourself that this thing should just be the identity. Unless, k is not equal to L, then, then it's 0. But that we get for free. We already know that. So basically, we just want to, ensure that this is the identity. And in fact, it is, because you can just act with this on the vacuum state. If you act with it on the vacuum state, then this term just gives us 0, right? And then when you act with this term, well, you pop a particle in, you pop one out. That can't do anything to the state. And so that's just spits back out the vacuum. So that's basically the idea. There might be some freedom of choice in the overall phase of this. So I'm actually not entirely convinced you couldn't put something like this here. That's something to think about. But in any case, it's perfectly consistent to have this phase be 0, and then you would just have this. But you see, the idea that these things are generated by a basis of single particle states actually gives you some constraints on what the possibilities are, because you should be able to move from one basis to another basis, and that shouldn't mess up the sort of commutation properties of these creation and annihilation operators. It's independent of what basis you choose for the single particle states. So, both these A's and these B's, right, will obey these sort of foundational things. So in a lot of books, these are just stated sort of without much proof. They're like, this is what they are, and that's just what it is. But it's nice to sort of play around with them a little bit and see why these are sensible things to do, sensible definitions. And again, the primary aspect of this, right, is just that if you put particles in some order, it shouldn't matter what order you put them in if they're identical. The only thing that can do is introduce a phase in your wave function. And we saw early on when we started this section that at least in 3 dimensions, you can make a choice that the only phases that you can get are either no phase or you get a minus sign. And that's the fermions and the bosons. All right, any questions about that? That's a little bit of review. Just okay, I'm gonna clear this then. All right, so we're gonna talk about operators today. How do operators work on these spaces? And we already looked at one. We already looked at the single particle operator. And we argued that the general form of that is going to be a sum over single particle states I and j, some coefficients ij, and then we have a I dagger aj. And so any single particle operator can be written like this with the appropriate choice of coefficients. So yeah, and we looked at some special ones, for instance, the number operator that just counts up the total number of particles we had. And that one just looks like that, right? You just sum up over the number of operators for each single particle state. You can show this is invariant under a basis transformation. That should make sense. If you have some fixed number of particles, it doesn't matter which basis you use for this single particle states to count them up. So that's important. And the other thing is these guys here, what they are is just the ijth elements of the single particle operator that you're interested in. So this is, again, the operator that we would normally just have act on a single Hilbert space. This is that generalization of that to the second quantization formalism. And it's easy to understand why this might be. This is, you take a particle and you remove a particle in state J and you add one back in state I. So this describes transitions between states J and I for a single particle, right? Because we pop one in, pop one back pop one out and pop one back in. So this is the single particle operator. And what's interesting is, of course, we can, I think this is where I left off. I wanted to use this operator and act on a two particle state, a particle state, ij, which what I mean by this is I pop in a particle in state I and state j into the vacuum. Just ask, well, what about this state? What if we take this operator and act with it? So let's see. We take this operator, act with it. And what we get, okay, so we're going to have a sum KL, H1 KL, and then we have a K dagger, AL, and then we have a I dagger, a J dagger, acting on 0. So what does this do? Well, in situations like this, what you want to do is start commuting operators around. What you want to do is you want to take all of the annihilation operators and move them as close as you can to, well, you want to move them right next to the 0. Why do you want to do that? Because as soon as one of those annihilation operators hits the vacuum, you get 0. So then you know that you're done, basically, that you just commute that through. So that gets rid of one of the operators. So okay, and if we were to do this, well, you'll have practice doing this on the homework, this kind of thing, using the commutation, anti-commutation relations to move the operators through. I'll do the details of this one and maybe in recitation, but you can show that what happens as you commute this through, what you get left with is HKI terms, and then you have a KJ state, meaning this is the vacuum acted on by a K dagger, a J dagger. And then you have plus or minus H KJ KI. And the two different signs are for the fermions and the bosons. So yeah, so what does this do? It essentially just acts on a single piece of this two particle state, the I and the J piece, independently. And then for the fermions, there might be a relative phase difference for the operator acting on one particle and then the other one. But otherwise, it just acts on each piece of that ket independently. So that kind of makes sense. And the minus sign also kind of makes sense because if you work this out, right, the I and the J states get flipped You see, this is a J and this is an I, so that they kind of get flipped there. And so for fermions, if you exchange the two, then you pick up a minus sign, and that's where the minus sign comes from. But otherwise, these things, these single particle operators, again, they work just like they would for, what we would expect them to do on single particle states, which is just all right. So just look like that. All right, so that's single particle operators, and now we can do something more complicated and look at multi-particle operators, two-particle operators, and so on. Any questions about that, though? I'll show you some of these commutation relations later, but I'm saving this one for recitation, or, yeah, and you'll practice it on the homework, just using permuting this through. But yeah, any questions? All right. So two particle operators. So two particle operators, well, this would be an operator that depends on, right, the numbers of particles in two different states. For instance, it would take two particles, right, in state I and J. It would remove them and pop in two more particles in some other states. That's basically the idea of a two particle operator. And to start with that, we might consider the pair distribution function, or the pair distribution operator. And this counts the number of particles in two different states. And what it is, so it's, you take Pij, and then what would you want? Well, you would want to take the number of, so this is the total number of ways of picking two particles in different states or in the same state. So you have an I and J. So this would be if you have n particles in state I and n sub j particles in state J. The total number of ways of picking. You can imagine these sort of bins or something. This is the bin that corresponds to state I, and this is the bin that corresponds to state J, and you have some number of particles in each one. Then the number of ways, right, of picking two particles, one from here and one from here, there's Ni here, and then there's Nj here. So total number of ways must be just the two numbers multiplied together. On the other hand, if they're in the same bin, if you want to pick out two particles from the same bin, you pick one out, but then there's no longer n sub I left, there's n sub I minus 1 left. So if you're in the same bin, then you need to subtract off this, right? Because if I is equal to j, then you would want this to be equal to ni times ni minus 1. So this just counts the number of ways of picking two particles out from two states, or from the same state, which is what this thing's about. And if you were to write this in operator notation, I mean, in terms of creation and annihilation operators, well, you can show that once you plug, and we know what these are the I dagger, AI things. You can show that this thing is actually a I dagger, a J dagger, a J, a I. And you can use the commutation relations to figure that out, right? You would just, here you'd put AI dagger AI, and here you put AJ dagger AJ, right? And then here you put minus delta IJ, AI dagger AI, and then you would start commuting stuff, and then this term gets canceled, and you get left with this. And you see this operator is nice because it's got all the annihilation operators out on the right side. This is what you would normally, we'll talk about this later, is called normal ordering, where you try to use the commutation relations to push all the annihilation operators to the right side. Again, why? Because remember, everything is constructed in terms of the vacuum. So you want your operators such that all the annihilation stuff is on the right, because that's what will act first on the vacuum. And we know that all those give you 0. So it's that's how you simplify these things. Okay, so how do we use this? Well, we can use this to create a kind of mutual potential energy, right? We could count up, say, the number of, we could add up the energy corresponding to interactions between particles in state I and J, right? And what would that be? Well, that would be some matrix element, Vij, right? Times the number of different ways of pairing together the two particles. So times this pair distribution operator, because that'll count all the total number of interactions you have between two particles. So a two particle operator then would look like this, right? We would sum over all the two states, and then we would have some matrix elements corresponding to the interactions between those two states, and then we would just have the projection operator. So this would be AI dagger, AJ dagger, AJ, AI. So what does this do? It just says, well, there's going to be a Pij number of different ways of picking two particles out of those two states, and that's the same as the number of pairwise interactions between those two particles, and each one of those pair interactions contributes some amount of energy, Vij. That's what this operator means. But of course, that assumes that your single particle basis is chosen to be the special one which diagonalizes that interaction. So just as in the single particle operator case, this, of course, in an arbitrary basis generalizes. And if it's no longer diagonal, then the most general kind of operator we can have, right, is one in which we have sum over 4 different indices, and it looks like this. We have AI, AJ, dagger, but then we could mix different states, so we'd pop them out in different states. So this, you can also derive this by just thinking about what happens to with a basis change here, right? You could do a basis change, and then this is the kind of form you'll get. And the key is, what's important to recognize, that these matrix elements, these Vijs, what they correspond to is just the two particle expectation values between operator V and two different two particle states, like this. And it's very important that this ordering is different for these A's. See, these A's are written as AKAL, but the matrix element is LK. This means that this is particle 1 in state L and particle 2 in state K. And this is a transition. This is matrix element corresponds to transitions, right, between particle 1 in state L, particle 2 in state K, and particle 1 in state I and particle 2 in state J. So these are the two particle states. And it's important that these annihilation operators are written in opposite order. That first you pop in a particle in state L, that's that first particle, and then you pop one out in state K. Sorry, you pop out the first one in state L and pop out the second one in state L. Then you pop one in, the second one in state J, and the first one in state I. But of course, first and second doesn't matter because they're identical. particle is. But this ordering does matter in terms of getting things right, because it comes essentially from this. See, these are written in opposite order too. So if you do the basis transformation, you'll just get this. You'll get this particular order for things. So just something to keep in mind. It's important for the fermionic case especially, because remember that the order in which you write the states actually determines whether or not you get a minus sign. So you have to be careful of that. So again, any operator can be written, any two-body operator can be written like this. And then if you diagonalize it, then it'll look like that. And this actually allows us to introduce a kind of Feynman diagram for this, describing what happens. You can think of it as sort of space-time diagram. And what it looks like is just like this. You have particles in states K and L, right? And then they transition to particles J and I, pair interaction. And this is the matrix element that corresponds to that. So so there you go. That's the two-body operator. But yeah, so we'll do more of this. But any questions so far about the two-body operator? How it works? You see, it's quite similar to this. These are the one-body operators. So the matrix, the numbers here are these matrix elements in the one particle Hilbert space, right? For some operator. Well, two-body operators, same thing, except the matrix elements are for two particles. And this could be different, right? We don't have an analog of this for a single Hilbert space, right? We don't. There's no way to think about this kind of potential energy for a single particle, right? This is something, an intrinsic property of having two particles in states I and J. So it's like a different thing. It's a new kind of term we could add to our Hamiltonian when we have multiple particles. Okay. Sometimes it's nice to think about these elements in position space. Then it kind of makes a little bit more sense what's going on. So we can talk about position space. And in position space, well, the single particle operator is kind of easy to think about. We just put in some completeness relations, and we assume that maybe the interaction is diagonal in position space. And then in this case, you would just have the integral over R, and then these guys would be the wave functions associated with states I and J, and then this would be some position space representation of the operator, and yeah, like that. So that's pretty good. Again, these guys are just the wave functions. And the two-body one in position space, if it's, typically it will be diagonal in position space. This one depends on, you have to put in two completeness relations, one for each particle in your, well, it's not two, it's a two particle space. So there's two Hilbert spaces. So you need a completeness relation over both coordinates, for the first particle and the second one. So you'd have dr vector and then another integration over the other particle coordinate. And these guys are just going to be product states, right? They're ij is just a tensor product of particle 1 in state I and particle 2 in state j. So the wave function associated with that is just the product of the two wave functions. So you get, for the first particle, you get this guy, and then for the second particle, you get this guy, right? And then what is your v? Well, if your v is diagonal in position space, well, then it would just depend on the two coordinates of the two particles. This describes the interaction potential between two particles in positions r and r prime. And so this is the typical form then of these things. So that's what these matrix elements would be in position space representation. The two particle operator also has it has a kind of, you can see here it has a sort of asymmetry here. If you write it out this way, it's obvious that we can just change the order of these two guys. It doesn't change anything, right? We can relabel r and r prime essentially, right? And if we do that, then the particles 1 and 2 will just flip their states. So this thing, there should be a symmetry here, right? Where you just flip, because you were integrating over all of them, so you could relabel this one as prime and this one not prime. It should be the same integral. So there's a symmetry here. Namely, you can just flip the states of the two particles. It's the same as exchanging, and this one's prime here. It's invariance under sort of relabeling r and r prime. I mean, so unless there's something funny with this v where it depends on, so typically this thing, right, this will only depend on, the distance essentially between r and r prime, right? That's the typical kind of interaction potential we would have. All right, so what are some examples of these position space operators? For this guy, an example might be Coulomb repulsion. And for Coulomb repulsion, the operator would be just 1/2 sum over, these are now sum over the particles that you have of e squared over Ri minus Rj. So that's a possibility. The single particle operators are just like whatever the single particle energies are, like kinetic energy for each particle and things like that. But the two-body operators allow you to introduce things like Coulomb interactions between two different charged particles. And in position space, it's kind of easy to write down. These operators this is just the sum over all of the pairwise interactions, right, that you have between particles I and j. There's no self-interaction in this case because, you only care about two different particles, I and j. So, this could be a possibility for the potential. For a two-body potential. But we'll see more examples later, I guess. But it's just, this is a common one, Coulomb interaction. Any questions? So we haven't, so these are just these matrix elements, which again are just thinking about the 1 and 2 particle spaces. But of course, we can use the position space representation for the whole second quantization procedure. Remember these states I here, a sub I, this pops in a particle in state I. But there's nothing preventing us from using, say, momentum or position to do that, to label those things. It's just we have to be careful, right? Because we know that those states are not proper states in the Hilbert space, right? They can't be normalized. So I have to be careful with that. But otherwise, it's just like when we did wave mechanics and talked about it, we have the idea of a free particle wave function that's not square normalizable, but we can still use it. And as long as we're careful about that, then things are okay. And the similar thing happens here, is that instead of states I, which are going to typically be energy eigenstates, we can instead use a different basis, namely the position space basis, and we'll do that. And that'll lead us to a discussion of field operators. And field operators are nothing but the position space version of these creation annihilation operators. But before we do that, I wanted to actually have some practice with doing this kind of commutation stuff. So before we jump more into position space, I want to talk about an important theorem associated with commuting around these creation annihilation operators, and that's called Wick's theorem. But yeah, any questions about this stuff before I clear? So Wick's theorem is important because in the end, what are we doing? Well, if we're trying to make some predictions for observables and things like that, we always end up wanting to take expectation values. And remember, everything is reduced to creation annihilation operators in the vacuum state. So the only ever kind of expectation value you ever care about is an expectation value of a bunch of creation annihilation operators sandwiched between two vacuum states. So you might have something like, something like this. And there might be a lot of these guys in here and lots of different indices. And you want to be able to evaluate things like this. And again, the idea is that any one of these, right, we can interpret as some multi-particle state, right? And then this is like some other multi-particle state, right? And so any expectation value between any operator, right, phi and a psi, for any multi-particle state, I can always reduce this to one of these guys with, maybe a whole lot of creation annihilation operators, because I can construct this guy from, a bunch of creation operators acting on the vacuum, popping in as many particles as I need, or even doing linear combinations of them if I must, if I have some entangled state. Same thing here. I can make this out of some creation operators acting on the vacuum. And then I know I can write any A operator in terms of the creation annihilation operators also. It could either be a one body operator, two body, could be arbitrary numbers. And in the end, all of these things will reduce to sums of terms that look like this, right? there might be a bunch of them. We might have like a sum over here with different coefficients, right? But in the end, everything you do in second quantization reduces to expectation values of creation annihilation operators sandwiched between vacuum states. So what's the theorem? The theorem is, we suppose let A be either AI or AI dagger. So we're just going to denote any of the creation or annihilation operators as some A. And it could be fermions or bosons, doesn't matter. The theorem is as follows, that if you have a product of these A's, n of them, say, then maybe I'll use a little n. Then this product can be written as a series. And what is the series? The first term in the series is the normal ordered product. This means normal ordered of A1, A2, A3, all the way up to AN. And again, what does normal ordering mean? It means you just put all the annihilation operators on the right and all the creation operators on the left. So an example might be normal order, say a I dagger, a J, a P dagger, a L. What this is, you just you identify the annihilation operators, they're right here. And then without messing up their sort of relative order, you just put them over on one side and you put all the other guys on the other side. Like that. That's what it is. Just that product. So it's a little bit like time ordering, sort of. Not really, but it's, again, people sort of got confused about this last time. You literally, if something is normal ordered, then you just rearrange the things in there such that it's, all of the annihilation operators are on the right and all the creation ones are on the left. That's what it means. That's equal to that. So normal ordering of this is just this, right? Okay, but these can't really be literally equal to each other because you're going to be missing all of the commutation relation pieces necessary to bring that product of operators into the normal ordered form. So you're going to be screwing up by some amount. And the amount you screwed up can be written as a series of contractions, as it turns out. The first correction you get is a sum over all j less than k of, there's a -1 here. That's the -1 depends on the whether you have fermions or bosons. If it's bosons, there's no -1. Otherwise, you'll get a -1. And so that's another important thing. So this is true for bosons. If you have fermions, it's a little bit more subtle because the normal ordering will depend. There will be an extra minus sign that you get if you have to permute the operators past each other an odd number of times. So if it takes like 1 permutation or 3 permutations, little exchanges of the operators to get there, then you pick up a minus sign in the case of fermions. That just comes directly from the anti-commutation relation. So for fermions, for instance, if we take the normal ordering of the operator AI dagger, AJ, AK dagger, what would this require? Well, this would require us permuting these two guys, right? And if we do that, then, well, we'll have to pick up a minus sign because that's one exchange. So for fermions, the normal ordering of this would be AI dagger, AK dagger, AJ with a minus one. So you normally put a P there to indicate that's the number of permutations it takes to get at the normal ordered state. So there's these extra minus one factors. If there were another operator here, like AM dagger, then you wouldn't have a minus sign because that would take two exchanges, right? You would have to move the AJ past the AK dagger and past the AM dagger, right? If you have an AM dagger in here too. So then you wouldn't have the minus sign. Okay. So what is this first correction? The first correction is you got this permutation where well, I'll first write it. It's the contraction between operators AJ and AK. And the contraction is, when I write this, what I mean by that, it's the vacuum expectation value between AJ and AK. And then that's not it. This is times the normal ordering of the rest of the operators. A1, AJ minus 1. So you extract out two of the operators, J and K, such that, and you do it for all pairs, all unique pairs of J and K. And the first term is the normal ordering of the rest of the operators times the contraction. The vacuum expectation value is just a number between those two operators that you've picked out. And then see, these are the rest of them. So I've extracted out the AJ and the AK, and then everything else is the same. It's just a normal ordering of the rest of them. And what about this factor of P? The P is the number of exchanges it takes to bring the operators AJ and AK next to each other. So this is the number of moves to get to AJ, AK together. So they're apart, you pick any two of them in that chain from A1 to AN, and then you do the little permutations, you exchange operators that are next to each other, and you count up the number of steps it takes to bring those AJ and AK close next to each other, and then that gives you whether or not you have a +1 or a -1 in the case of fermions. So again, the -1 and the P is just in the case of fermions, and it always just counts the number of steps it takes to get to the state that you want. In this case, it's having AJ and AK next to each other. So however many steps. That's the first term. Then the next term, unsurprisingly, is two contractions. It's all the ways of picking two pairs of states. So it's over all the pairs, let's call it JK and LM, right? And what is it? It's, again, -1 to the P, and this would be the number of steps it takes to get the two individual pairs next to each other, the J next to the K and the L next to the M. and then it's contractions of a j a k a l a m, and then it's the normal ordering of the rest of the things. Everything except the ones that we took out, right? So AJ, AK, AL, AM, right? And you keep going until you have paired off everything. So you have one pair, right? Then you have two contractions, then three, however many it takes, until you're just left with one operator, right? And then the normal ordering of one operator is the operators. Or you have a normal ordering of two there's two options, even and odd, right? You just keep extracting two operators until you get to the end, and in the end you're either left with one operator if you had an odd total to begin with, or you're left with two operators, in which case that's easy. You just normal order the last two operators. All right, well, it's zero because remember the normal operating procedure puts all the annihilation operators on the right. So if there are any annihilation operators at all, even just one, then you're going to get whatever all these daggers are, and then you're going to get AI acting on zero out here. So that's automatically zero. And so the only other case you have to worry about is if there are no annihilation operators whatsoever. But if there are no annihilation operators, well, of course, that's also going to be zero, because you're just going to be popping in a bunch of particles in different states and not popping any out. So you're going to have an inner product between some multi-particle state with a bunch of particles in it and then the vacuum. So that's just going to be zero. That's also zero. So you don't get anything other than zero. Okay. So why is it useful? Is because if you take the vacuum expectation value of any product of creation annihilation operators, what's the only term that's left over? Well, it must be the one that doesn't have any normal ordering left anymore, right? And the only term that's left over that doesn't have any normal ordering left is the one where everything has been contracted. So another way that the Wick theorem is sometimes stated is that the vacuum expectation value of any product of these creation annihilation operators is equal to the sum over all possible pairwise contractions of the operators. So this is why sometimes you have, say like this, you would say, what's this? Well, it must be all the different ways I can pair off these operators. So here's one way to pair them off. Here's another way to pair them off. And here's the last way to pair them off, right? And so this thing is equal to A1, A2. And again, these are just the zero expectation values. A3, A4 plus A1, A3. A1, A3, A2, A4. Right, we got 1, 2, then we have 1, 3, and 2, 4, and then the last one is 1, 4, and 2, 3. But for fermions, you have to be careful. Again, you want to put in minus signs if it takes an odd number of exchanges to bring the two things you're contracting together. So here, they're already together, so you're good with this one. This one, though, we have to exchange 2 and 3. We have to flip them so that A can get paired off with 3 and 2 can get paired off with 4. So this one has a -1 sign for fermions. Okay. And then this last one, well, the 2 and 3 are together, so that's fine. So we need to get the A1 and the A4 together. So what do? We'd bring the A1 and we bring it over once. We bring it over twice. That's 2 times, so we don't need a minus sign. Okay, so that's Wick's theorem. It lets you construct these kinds of things. But sometimes you want to know what the full operator is. You don't want to take the expectation value. So that's kind of useful too, the rest of these terms. Again, if you're taking the vacuum expectation value, because the normal ordering things just all give you 0, what you're left with is just that last term where everything has been contracted off. So let me, this is not very clean anymore because I put a bunch of stuff here, but let me get rid of the extra stuff so I can box the actual Wick's theorem. This is enough, I think. Let me give it a little box. Here's the box. This is Wick's theorem. All right. So product of any creation annihilation operators, the normal ordering version of it, and then all the contractions, starting with 1, 2, all the way to the end where everything gets contracted off. And I won't prove this theorem. I used to assign this as an extra credit to prove the theorem. It's usually in the appendix of grad quantum books. I don't think the proof is particularly interesting. It relies on properties of the vacuum state, clearly, because the vacuum state is special here. I mean, the reason this works is basically what happens is to get the normal ordered state, you have to put in a bunch of commutation relations. And then those commutation relations give you extra terms. And those extra terms are only there if these contractions give you a non-vanishing thing. So, right. For instance, for bosons, right? Everything's okay. You can commute everything around as long as the annihilation, as long as you don't have as long as you're not trying to commute these two guys, right? Because if you try to commute these guys, then you pick up an extra term, because we know that these guys give the identity for boson. So and that's what these contractions basically do for you, is they keep track of all that. Anyway, any questions about Wick's theorem? Okay, I think next time I'm going to do another example of applying this to fermions, because it's sort of the hardest case because of all the number signs, of all the minus signs and stuff. But I don't know. This is a good place to stop. Very important theorem for doing second quantization calculations. And next time we'll also get to field operators, where we're going to take these creation annihilation operators and instead pop particles in and out at some location or with some momentum. And that actually that's what a quantum field essentially is, as we'll see. That's how you get to quantum field theory, basically.